on May 29, 1953. At 11:30 a.m., a New Zealander named Edmund Hillary and a Nepalese Sherpa, Tenzing Norgay, became the first explorers to reach the summit of Mount Everest, the world's highest peak at 8,848 meters above sea level. The base camp was set up on March 20th at the Khumbu Glacier, which is at a height of 5,425 meters above sea level. And it took them about 2 months to reach the peak of Mount Everest. The extreme weather throughout the journey makes Mount Everest expeditions a very daring feat. Consider this mountaineering expedition as a thermodynamic process where the explorers are traveling from an initial state, that is their base camp, and finally reaching the peak, that is the final state. There are certain values and terms that are used to describe the conditions of the explorers before and after reaching the top of Mount Everest. Initially, they were at 5,425 meters above sea level, and finally they were at 8,848 meters above sea level. That is, their position changed after the process. Also, the initial date and final date give us an idea about the time in which the process started, the time it ended, and also the time it took to complete the process. All of these data, the initial, final positions, the dates, etc., give us some information about the state of the explorers. So in this case, the position and date can be considered as state variables. Thermodynamics is a field of science that not only explains how or why certain processes take place, but also helps us to predict whether a process will happen or not, and if it happens, what the final state of the system would be. For all these applications, mathematical calculations are required, which include certain state variables. In simple terms, state variables can be defined as a measurable quantity which gives certain information about a system which is in equilibrium. The equilibrium state of a system can be thought of as the system doing absolutely nothing. A system will be in a state of equilibrium before a process, and during the process the system will be in various non-equilibrium states. When finally the process is over, a new state will be achieved with a new equilibrium. This is when the state variables can be measured again. State variables are macroscopic in nature, meaning that they describe the state of the whole system, not the state of atoms or molecules present in the system. They are also independent of the path. This means that the state of the system depends only on the initial and final values, and we are not interested in how the state was achieved or what path the system went through to achieve it. For a gaseous system, the state variables that give information about the equilibrium state would be volumes, pressure, temperatures, the number of moles of the gas, and the composition of the system as a mixture of different gases. For example, consider a jug of water kept at room temperature. The water is poured into different glasses unevenly. Will the temperature of water be different for the different glasses? No. What about the volume of the water? Yes, obviously. The water volume for each glass is different. So in conclusion, some variables change according to the size of the system and some don't. State variables that do not depend on the size of the system are called intensive variables. For example, temperature, pressure, density, etc. are intensive variables. Whereas those variables that depend on the size of the system are called extensive variables. Volume, internal energy, number of moles, total mass, etc. are. The equation of state is a mathematical relation that connects the state variables of a thermodynamic system at equilibrium. The equation of state for real gases, liquids and solids are very complicated. So, in order to simplify our analysis, we will consider a simple case or an ideal case first and add complexities later. The equation of state for an ideal gas is given as PV is equal to mu RT, where P is the pressure, V is the volume, mu is the number of moles, R is the universal gas constant, and T is the temperature of the gas. From an ideal gas equation, we can see that for a fixed number of moles of a given gas, there are only two independent variables, P and V or T and V. The pressure volume curve of a gas at constant temperature is called an isotherm. The equation of state of an ideal gas, also known as the ideal gas law, is a combination of three gas laws: Boyle's law, Charles' law, and Avogadro's law. So far, we have understood that during a thermodynamic process, the system is not in equilibrium. Once the process is over, the system finally comes into an equilibrium state. Also, the state variables are defined for the equilibrium state. So how can we describe a thermodynamic system that is undergoing a thermodynamic process, or a system which is in the middle of some process? This is what we will tackle next. So let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.